There are many types of RAID, as shown by the myriad versions available. RAID 0, RAID 1, 5, 6, 1 plus 0, and on and on and on. You rarely see 2 through 4. Those are parity types of RAID that have been completely eclipsed by 5 and 6, so you rarely see those. And while they are all redundant, not all are truly fault tolerant. Redundant means that you have more than one. Fault tolerant means that you can survive a failure and still get access to your data, and that's what you want. For example, RAID 0 is not fault tolerant. RAID 0 is just known as striping. You stripe data across multiple drives to increase speed and performance. So we don't really use RAID 0 if we want something fault tolerant, because if one drive was to fail, we would lose all of the data. Instead, we'll go for RAID types such as RAID 1, which is mirroring, and RAID 5, which is striping with parity. These are very common types of fault-tolerant RAID. They can survive a fault or a failure and keep supplying data to the users. Let's describe those two in a little detail now. RAID 1 is known as mirroring. It requires 2 drives, which should be of the same make and model. For example, you would want the same Western Digital drives within the same Blue series. All data is written to both of the drives. It's mirrored. If one drive fails, then the other continues to function, offering that fault tolerance that you want. Data is normally read from only one drive. So in that respect, you get the same performance as you would in a single drive system. But when you write the data to the mirror, it takes a little longer because you're writing to 2 drives at the same time. Let's show an illustration of this. Here we have 2 disks, disk 1 and disk 2, each of which are 500 gigabytes, and they're connected to a RAID controller. And quite often the controller is just an adapter card, could be a PCI Express by 1 card, or it could be an integrated device within your motherboard. When the mirror is created, the 2 drives basically become one. They're collectively known as a single volume letter. In this case, we chose M for mirror, but you can choose whatever letter you want as long as it's not been used yet. One of the issues you might find with RAID 1 arrays is that the controller acts as a single point of failure. And so you could create a new configuration where each disk is connected to a separate controller. And this is known as disk duplexing. So you have even more fault tolerance at this point. RAID arrays can be controlled through hardware or through software. An example of hardware would be using a RAID adapter card, as we mentioned before, or a RAID-enabled motherboard, and the array is created within the card or the motherboard's firmware. This is done outside of the operating system. An example of software would be to create the array in compliant versions of Windows, say within the disk management console window. Let's show an actual RAID 1 array that was created within Windows, and then we'll show one that's created in firmware on a separate system. Here's an example of a RAID 1 array controlled by software in Windows, and it's controlled within the disk management console window. Here we have our list of volumes. For example, the C volume, which is on its own hard drive, and that's where the operating system lives. And then we have the M volume, which is the mirror, and that is comprised of 2 other disks, disk 2 and disk 3. And you can see here the reddish-brown header indicates a mirrored volume. So M is the mirrored volume. Any data that is written to this volume is written to both drives simultaneously. When it's read from the volume, it just reads from the first volume in the mirror, disk 2. If one disk was to fail, and most likely that's the lower number in the mirror, disk 2 would probably be the first to fail. But if that was to fail, then the mirror would be broken. However, users would still be able to read and write data from disk 3. The M volume would continue to function, and that is the fault-tolerant portion of RAID 1. But we would need to fix it. We'd need to replace that disk 2 physically, and then rebuild the mirror, which would then copy all the data from disk 3 to disk 2, and then it would resynchronize, and then we would have our mirror back. Now, here's an example of a RAID 1 array controlled by firmware. This is Intel Rapid Storage Technology. It's a built-in RAID controller within the motherboard. This motherboard can handle RAID 1 and can do RAID 5. In this case, I have a RAID 1 array. There's 2 Western Digital drives working in concert. Each one is 1 terabyte. It shows up here as 931 gigabytes. And it shows you that it is indeed a RAID 1 mirror. If this mirror was to break, if it was to fail, we would have to fix it here. We would have to do recovery here and not in Windows. If we were to take a look at the volume that was created for this RAID 1 mirror in Windows, in disk management, we would see it would just be 1 drive. It would show up as 1 disk, not as 2, as you can see here. This is the disk management window again. Data E is that mirror, but it only shows as 1 disk. So you don't actually know that you have a mirror running here if you look at it from Windows. You would have to look at the disks individually within the BIOS or within the firmware. And again, if it was to fail, you'd have to rebuild it within the firmware itself. And to get into that firmware, for Intel, it's usually Control-I, and you press that before you would even get into the BIOS. You know, your F2 to get into an Intel BIOS. You press the Control-I to get into the firmware for the RAID adapter before that. And that's, again, Control-I. So that's RAID 1. Now we move into RAID 5, which is known as striping with parity. With RAID 0, you stripe data across multiple drives to increase performance. And you do this with RAID 5 as well. But now we also use parity so that in the event of data failure, we can use the parity information to recreate that data. It requires a minimum of 3 drives, which should be of the same make and model. RAID 5 arrays often have 3, 4, or 5 drives, but you're not limited to that. I believe the normal maximum for hardware and software is 32 drives. Data is striped across all drives, regardless of how many drives you have. Again, it's done in an effort to increase performance. Parity information is distributed across drives in a staggered format. This is known as distributed parity blocks. Any block of data also has a calculated amount of parity, and that's for repairing the data if that particular drive fails. This parity information is distributed among all the other drives, except for the one where the data was written to. So in this scenario, the data is divided into 3 parts, A, B, and C. Let's imagine that we have a 384 kilobyte file that we want to write to the array. Well, that's going to be written in blocks to each drive, one at a time, and each of these blocks would be 64 kilobytes. So for example, drive 1 and drive 2 will be written to, and A1 is a 64 kilobyte block. A2 is another 64 kilobyte block. And these are also sometimes referred to as chunks. Together, they are a stripe of data. And it continues in that manner. The next 64 kilobyte block would be B1 and B2, but this time they're written to drive 1 and drive 3. And then the C block of data, C1 and C2, which are written to drive 2 and drive 3. In total, we have 6 blocks of data, and if you multiply that by 64 kilobytes each, that gives us our total of 384 kilobytes, which is the size of the file. The parity for each stripe of data is placed on the remaining drive. Now, in an effort to protect the data in the event of failure, we're using this parity. So parity for each stripe of data is placed on that remaining drive for each letter, for each set of blocks, basically. And you can think of parity information as a sort of compressed version of the stripe of data. So the A1 and A2 stripe of data has a parity version on drive 3, which we will call AP. The B1 and B2 stripe of data has a parity version on drive 2. We'll call that BP. And the C1 and C2 stripe of data has parity on drive 1, and we'll call that CP. You'll notice that the parity blocks are staggered. It starts with drive 3, then drive 2, then drive 1. You don't want to have all of the parity on one drive. So this way, we can recreate any data block or portion of that data block if it fails, or if an entire drive fails. So again, in a RAID 5 environment, one hard drive can fail, and you'll still be able to get access to the data, and we can still recreate the data once we replace that drive. But if a second drive was to fail, you'd be in trouble. That's why there's RAID 6. With RAID 6, you have additional parity, and up to 2 drives can fail while still being fault tolerant. So you have to decide, how much fault tolerance do we need? How much money do I have for hard drives? And that will help you decide whether you're going to use RAID 5 or RAID 6. Here's an example of a RAID 5 array that is controlled by software. It's running in Windows in the disk management window. And we have our 3 drives here. They're labeled as disk 1, disk 2, and disk 3. Collectively, they make up the S volume. And that light blue, that baby blue in the header means RAID 5 volume for this operating system. If you write data to this volume, it is striped across the 3 drives. But parity information is included as well for each data block. If one drive was to fail, you would need to replace that drive and then rebuild the array within disk management and rebuild the data on the new drive. Or you could attempt to restore from backup. Now, software is great, but hardware is always superior. And you're definitely going to see hardware-based RAID 5 arrays. And here's an example of some hardware that you might see used in the array. There's a controller at the top, which can handle as many as 5 drives, and it's an SATA controller. And on the bottom, we have 3 hard drives that will be connected to the controller. And again, you have to have 3 drives minimum, and they should be the same make and model. The controller's firmware can be accessed previous to the operating system being booted, in the same manner that we pressed Control-I to get into the RAID firmware on the Intel motherboard. But again, you want to make sure the make and model of the hard drives is the same. And if you look closely at these 2 drives, you'll see a slight difference. One is a 1600 AVBS, and the other is a 1600 AVJS. They're both 160 gig drives, but they're slightly different. And I think the one difference with these is the cache memory on board. And that could be a big deal. You could try it, you could see if it'll work, but it's not really a good idea. In addition to that, you see the drive on the left has been written on. That's always a bad sign as well. So when you're working with hard drives, work with new drives. Don't just grab anything you can find that's already been used. You don't know the condition of that drive. You want to use new drives and know that you're going to have a shelf life of, say, 2 or 3 years for those drives. And you want to know that they're all new, newly formatted, and brand new out of the box. So watch out for any drives that have been written on. Watch out for slight changes in the name, slight differences. Make sure you're using the same drives, manufacturer and model. And that's about the end of this sub lesson.